right now, at this very moment, about 1% of the static on an untuned television set is coming from the edge of the observable universe, not from a satellite, not from a cell tower or a radio station or anything built by human hands. That faint, random hiss is the afterglow of creation itself, light that has been traveling for over 13 billion years, stretched and cooled and diluted until it is barely a whisper against the silence of space. And if you could see it with the right instruments, if you could peel back the noise and reveal the signal underneath, you would be staring at the oldest photograph ever taken, a portrait of the universe when it was just 380,000 years old. An infant. And encoded in that portrait, like a fingerprint pressed into wet clay, are the answers to nearly every question we have ever asked about the cosmos. How old is it? What is it made of? What shape does it take? Where did the galaxies come from? Where is it all going? This is the cosmic microwave background, and it is, without exaggeration, the single most important observation in the history of cosmology. It has been measured with such precision that we know the age of the universe to within less than 1%. It has revealed that ordinary atoms, the stuff of stars and planets and human beings, make up only about 5% of the universe's total energy content. It has shown us that 27% is dark matter, an invisible substance we have never directly detected. And the remaining 68% is something even stranger, dark energy, a mysterious force that is accelerating the expansion of the cosmos. All of this from a faint microwave glow that you can pick up with a cheap radio antenna. But to understand what this light is and what it means, and why it has consumed the careers and imaginations of generations of physicists, we need to go back. Way, way back, to a time before stars, before atoms, before the universe was anything you would recognize at all. We need to go back to the beginning. And the beginning was hot. Unimaginably, incomprehensibly hot, a fraction of a second after the Big Bang. The temperature of the universe was measured in trillions of degrees. At this temperature, matter as we understand it simply did not exist. There were no atoms, no molecules, no crystals, no rocks, no gas clouds. There was instead a seething, roaring ocean of fundamental particles, quarks and leptons, gluons and photons, all slamming into one another at nearly the speed of light. Energy and matter were interchangeable in these conditions, conjured from one form to another and back again, in an endless frenzy of creation and destruction. Pairs of particles and antiparticles materialized out of pure energy, existed for a fleeting instant, and annihilated back into radiation. The universe was a furnace of such intensity that the very distinction between matter and energy was blurred beyond recognition. And the universe was expanding rapidly. Space itself was stretching outward in every direction, thinning the density of this primordial soup, and critically cooling it down. As the temperature dropped, the chaos began to organize. In the first millionth of a second, quarks combined into protons and neutrons, the building blocks of atomic nuclei. This transition, called quark confinement, happened at a temperature of roughly 2 trillion degrees, when the strong nuclear force became powerful enough to permanently bind quarks together into composite particles. Before this moment, quarks roamed freely. After it, They were locked inside protons and neutrons forever. And then something remarkable happened. About 1 second after the Big Bang, when the universe had cooled to roughly 10 billion degrees, the weak nuclear force, which governs the transformation of protons into neutrons and vice versa, fell out of equilibrium. The ratio of protons to neutrons was locked in at roughly 7:1. This ratio would turn out to be one of the most consequential numbers in all of physics, because it would determine just how much of each element the newborn universe would produce. A few minutes later, when the temperature had dropped to about 1 billion degrees, conditions were finally right for the first act of cosmic chemistry. Protons and neutrons began to collide and stick together, forging the nuclei of the simplest elements. First came deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Then helium-3, with 2 protons and 1 neutron. Then helium-4, the most stable configuration, with 2 protons and 2 neutrons, and trace amounts of lithium-7, a fragile nucleus cobbled together from the leftovers. This era, known as Big Bang nucleosynthesis, lasted only about 20 minutes. 20 minutes. In that brief window, the universe manufactured roughly 75% hydrogen and 25% helium by mass, with tiny sprinklings of deuterium and lithium. And then the window slammed shut. The universe had expanded and cooled too much for nuclear fusion to continue. The cosmic forge went dark, and here is something remarkable. The precise amounts of each element produced during nucleosynthesis depend critically on the conditions of the early universe, the expansion rate, the temperature, and above all, the ratio of ordinary matter to photons. A quantity cosmologists call the baryon to photon ratio. Change that ratio even slightly, and you get radically different abundances. More baryons relative to photons means more deuterium gets converted to helium. Fewer baryons mean more deuterium survives. The observed abundances of these light elements in the universe today, measured in the most primitive, chemically unprocessed clouds of intergalactic gas, match the predictions of Big Bang nucleosynthesis with impressive precision, and the baryon to photon ratio needed to make those predictions work is exactly the same ratio independently measured by the CMB. Two completely different observations, one from the chemistry of the first few minutes, and one from the temperature patterns of the photons released hundreds of thousands of years later, pointing to the same answer. That kind of concordance does not happen by accident. It is the hallmark of a theory that is capturing something deep and true about the universe. And here is a critical thing to understand. The universe at this point was still ferociously hot, measured in millions of degrees. And it was filled, wall to wall, with a blinding fog of radiation. Photons, particles of light, were everywhere, in extraordinary abundance. For every single proton or neutron in the universe, there were roughly 1 billion photons. 1 billion. The universe was not a place of matter with some radiation sprinkled in. It was a universe of radiation with a faint seasoning of matter. And those photons could not travel freely. They could not cross from one side of a room to the other, let alone traverse the cosmos, because the universe at this stage was a plasma, a state of matter in which electrons are stripped free from atomic nuclei and wander independently through space. And free electrons are extraordinarily good at scattering photons. Every time a photon tried to move in a straight line, it almost immediately collided with an electron and was sent ricocheting off in a random direction. Then it hit another electron, and another, and another. The photons were trapped, bouncing chaotically through a dense fog of charged particles, getting nowhere. The universe was opaque. If you had been somehow present at this moment, floating in this primordial plasma, you would have seen nothing, an impenetrable wall of white-hot light in every direction, blinding and featureless, the ultimate whiteout. And this state of affairs persisted for hundreds of thousands of years. Think about that for a moment. The universe existed for hundreds of thousands of years in a state where light itself was imprisoned, where photons could not travel, where the cosmos was wrapped in an unbroken cocoon of glowing plasma. But the expansion continued, and the cooling continued. And slowly, degree by degree, the temperature crept downward, until, about 380,000 years after the Big Bang, the universe crossed a threshold. The temperature dropped to approximately 3,000 degrees Kelvin, about the temperature of the surface of a cool red star. And at this temperature, something extraordinary happened. The electrons, which had been careening wildly through the plasma for hundreds of millennia, suddenly found themselves slow enough, cool enough, to be captured by the waiting atomic nuclei. Protons snagged electrons and became neutral hydrogen atoms. Helium nuclei grabbed their pairs of electrons and became neutral helium atoms. This process is called recombination, which is a slightly misleading name because the electrons and nuclei had never actually been combined before. This was their first union, not a reunion. But the name stuck, and cosmologists have been living with it ever since. Recombination did not happen all at once. It was not a sudden flip from opaque to transparent. It was a transition, unfolding over roughly 10 to 20,000 years, which sounds like a long time, but is a mere blink in cosmic terms. During this transition, the fraction of free electrons dropped rapidly. And as it did, the photons found it easier and easier to travel without scattering. The fog thinned. The mean free path of a photon, the average distance it could travel before hitting an electron, grew from tiny fractions of a light year to light years, to millions of light years, and eventually to infinity. The universe became transparent. And this transition, this relatively thin shell of time when the photons were released, is what cosmologists call the surface of last scattering. It is not a surface in the physical sense. It is a moment in time, stretched across space, from which the CMB photons began their long, unimpeded journey to our instruments. When we look at the CMB, we are looking back in time to this surface, this moment of liberation, seeing the universe as it was when it was roughly 380,000 years old, at a temperature of about 3,000 Kelvin, at a redshift of approximately 1,089. And recombination changed everything. Because neutral atoms do not scatter photons the way free electrons do. The photons of the universe, trapped for 380,000 years in that dense, opaque plasma, were suddenly released. The fog cleared. In a cosmic instant, measured in perhaps 10,000 years or so, the universe went from opaque to transparent. Light was free to travel. And the light that was released at that moment, the photons that were freed when the first atoms formed, did not simply vanish. They kept going. They have been traveling through the expanding universe ever since. For over 13 billion years, those ancient photons have been streaming through space in every direction, carrying with them a snapshot of what the universe looked like at the moment of their liberation. This is the cosmic microwave background, the CMB, the afterglow of the Big Bang. It is not the light of the Big Bang itself. It is the light of the universe at 380,000 years old, the moment when the cosmos first became transparent. It is a photograph, in a sense, taken from the surface of last scattering. The name physicists have given to this thin shell of space and time from which the CMB photons were released. Imagine it as the wall of a vast spherical room surrounding us in every direction, 14 billion years in the past. When we look at the CMB, we are looking at this wall, the farthest thing we can ever see with electromagnetic radiation of any kind. Beyond that wall, there is nothing to see. Because nothing existed there, but because the universe before recombination was opaque. The photons from those earlier times were scattered, absorbed, and re-emitted so many times that any directional information was scrambled beyond recovery. The CMB is a curtain, and behind that curtain lies the first 380,000 years of cosmic history, hidden from our view forever. At least, hidden from any telescope that relies on light. But what a curtain it is. Now, decades before anyone detected this ancient glow, a small group of theoretical physicists predicted it should exist. And the story of that prediction is, in its own way, just as remarkable as the discovery itself. It begins with a man who loved jokes almost as much as he loved physics. George Gamow was born in Odessa in 1904, then part of the Russian Empire, and he was brilliant, irreverent, and occasionally sloppy with his mathematics. As a young man, he made pioneering contributions to nuclear physics, including one of the first successful applications of quantum mechanics to explain radioactive decay. He showed that alpha particles could tunnel through the energy barrier of an atomic nucleus, a calculation that made his reputation and earned him, at the age of just 24, an invitation to work with Niels Bohr in Copenhagen. But Gamow was restless under the Soviet regime. He and his wife attempted to defect multiple times, including a dramatic failed attempt to cross the Black Sea by kayak, paddling 250 kilometers toward Turkey before being turned back by a storm. They eventually managed to leave the Soviet Union in 1933, attending a physics conference in Brussels and simply not returning. He fled first to London, then to the United States, where he took a position at George Washington University in Washington, D.C. By the late 1940s, Gamow had become fascinated with the question of how the elements formed. Where did all the hydrogen come from? Helium, the carbon, oxygen, and iron that make up our bodies and our world. Gamow suspected that the answer lay in the early universe. If the cosmos had been extremely hot and dense in its youth, perhaps nuclear reactions in those first minutes could have forged the elements. He recruited a young graduate student named Ralph Alpher to help with the calculations, and together they worked through the nuclear physics of a hot, expanding fireball. In 1948, they published a landmark paper titled The Origin of Chemical Elements. And here Gamow could not resist a joke. he added the name of the eminent physicist Hans Bethe to the author list, even though Bethe had contributed nothing to the work. The reason was purely for comedy. Alpha, Bethe, Gamma, a pun on the first three letters of the Greek alphabet: alpha, beta, gamma. Alpha, who was a young student trying to establish his own reputation, was furious. But the name stuck, and the paper has been known as the Alpha Beta Gamma paper ever since. The paper made important strides, but was flawed in some of its details. It suggested that all elements could be produced in the Big Bang, which turned out to be wrong. Only the lightest elements were forged in those first minutes, while heavier elements were cooked inside stars. But a related paper, published that same year by Alpha and his colleague Robert Herman, contained something far more enduring. Alpha and Herman realized that if the early universe had been a hot plasma, then the radiation from that era should still be permeating all of space. As the universe expanded, that radiation would have stretched and cooled, redshifted to longer and longer wavelengths. And by the present day, it should appear as a faint bath of microwave radiation filling the entire sky. They even estimated its temperature, roughly 5 degrees above absolute zero. 5 Kelvin, a prediction made in 1948 from first principles about a signal that nobody had ever observed. It is worth emphasizing how remarkable this prediction was. Alpha and Herman were saying that the entire universe should be glowing, faintly, uniformly, in every direction, at microwave wavelengths, that there should be a bath of photons filling all of space, left over from a time when the universe was 1,000 times hotter and 1 billion times denser than it is today. And they got the temperature roughly right, within a factor of 2 of the value that would eventually be measured. Their estimate of 5 Kelvin compares remarkably well with the actual value of 2.725 Kelvin, especially considering the crude state of cosmological knowledge in the late 1940s. And then nothing happened. The prediction was largely ignored. Radio astronomers told Alpha and Herman that the radiation was too faint to detect with existing technology. Gamow himself was not a strong advocate for the prediction, and by some accounts, initially dismissed its importance. The idea of a relic radiation field from the early universe quietly gathered dust in the back pages of the physics literature. For nearly 2 decades, nobody searched for it. Nobody built an instrument to look for it. The most important prediction in cosmology lay forgotten, while the scientists who made it watched in frustration. Meanwhile, across the Atlantic, the great debate about the origin of the universe was raging. On one side stood the proponents of the Big Bang theory, championed by Gamow and others, which held that the universe had a beginning, a single, hot, dense starting point from which everything expanded. On the other side stood the advocates of the steady-state theory, led by Fred Hoyle, Herman Bondi, and Thomas Gold, who argued that the universe had no beginning and no end. In their model, the universe was eternal and unchanging on the largest scales, with new matter continuously created to fill the gaps left by cosmic expansion. The steady-state theory was elegant, philosophically appealing, and deeply wrong, but in the absence of decisive evidence, both sides could claim legitimacy. It was, in fact, Fred Hoyle who coined the term Big Bang, and he meant it as a dismissal, a term of ridicule, an absurd cartoon of an idea, he thought. the notion that everything erupted from some primordial explosion. The name, like so many aspects of this story, stuck despite the intentions of its creator. Hoyle himself was a formidable intellect, a brilliant astrophysicist who would go on to make genuine contributions to our understanding of stellar nucleosynthesis, the process by which stars forge heavy elements in their cores. But on the question of the universe's origin, he was simply wrong, and he would spend decades resisting the evidence that eventually buried the steady-state model. By the early 1960s, the debate was unresolved. Both sides had their arguments, their supporters, their rhetorical strengths. What was desperately needed was evidence, a decisive observation that could settle the question one way or the other. And that evidence was about to arrive, entirely by accident, courtesy of two radio astronomers, a giant horn-shaped antenna, and a pair of particularly stubborn pigeons. Arno Penzias was born in Munich in 1933 into a Jewish family that barely escaped the Holocaust. He and his brother were sent to England on the Kindertransport in 1939, and his parents managed to follow shortly after, eventually reaching the United States. The family settled in New York, where young Arno grew up in the garment district of Manhattan. He went on to earn a doctorate from Columbia University, studying radio astronomy using masers, devices that amplify microwave signals with extraordinary precision. Robert Wilson was born in Houston, Texas, in 1936, the son of a chemical engineer who worked in the oil industry. A quiet, methodical Texan with a talent for instrumentation, Wilson earned his doctorate at Caltech, where he had studied under the guidance of radio astronomy pioneer John Bolton. Wilson's thesis involved using radio observations to map the Milky Way galaxy. He was a perfectionist, meticulous about understanding every source of noise and error in his instruments, a trait that would prove essential in the discovery that lay ahead. The two met at Bell Telephone Laboratories in Holmdel, New Jersey, where they had been given access to a remarkable instrument. The Holmdel horn antenna was a massive, horn-shaped receiver 20 feet across, originally built for satellite communications as part of the ECHO project in the early 1960s. It was designed to bounce signals off balloon satellites in orbit. The antenna had a distinctive shape, flaring outward like a giant ear trumpet laid on its side, and it was mounted on a rotating base that allowed it to be pointed at different parts of the sky. Its design was specifically engineered to minimize the reception of stray radiation from the ground and the antenna structure itself, making it exceptionally clean for sensitive radio observations. By 1964, newer satellite technology had made the ECHO system obsolete, and Penzias and Wilson seized the opportunity to use the antenna as a radio telescope. They planned to measure radio emissions from the Milky Way galaxy and from intergalactic space. It was, on the face of it, a straightforward astronomical survey. But from the very beginning, something was wrong. When Penzias and Wilson pointed the antenna at the sky and began collecting data, they found a persistent, low-level noise that they could not explain. It was a faint hiss, barely detectable, but it was always there, day and night, summer and winter. No matter which direction they pointed the antenna, it seemed to come from everywhere at once, uniformly distributed across the entire sky. They were meticulous. They checked every component of the instrument. They accounted for interference from New York City. They considered radiation from the atmosphere, from the galaxy, and from the sun. They looked at every possible source, and one by one, they eliminated them all. And then there were the pigeons. A pair of pigeons had taken up residence inside the horn antenna, and they had, as pigeons do, left a considerable mess behind them. Penzias and Wilson suspected that this accumulation of what they delicately referred to as a white dielectric material might be contributing to the noise. They captured the pigeons, drove them to a distant Bell Labs facility, released them, and carefully cleaned out the antenna. The pigeons came back. Pigeons do that. Eventually, the birds were dealt with more permanently, the details of which neither astronomer liked to discuss in public. And the antenna was thoroughly scrubbed. But after all of this, the mysterious noise remained. A steady signal at a wavelength of 7.35 centimeters, corresponding to a temperature of roughly 3.5 Kelvin, uniform, isotropic, inescapable. Penzias and Wilson were baffled. They had a signal they could not remove and could not explain. The answer was waiting for them just 60 kilometers away, at Princeton University, where a group of physicists was preparing to do the very thing that nobody had done since Alpher and Hermann's prediction in 1948. Robert Dicke, along with his colleagues Jim Peebles, Peter Roll, and David Wilkinson, had independently worked out that the Big Bang should have left behind a bath of microwave radiation. And they were in the process of building their own antenna to look for it. The connection was made through a mutual friend. Bernard Burke, a professor of physics at MIT, had heard about Peebles' theoretical work and mentioned it to Penzias during a phone call. Penzias immediately recognized the significance. He called Dicke at Princeton, and Dicke drove out to Holmdel to see the antenna and hear the signal for himself. The story goes that when Dicke hung up the phone after that first call with Penzias, he turned to his colleagues and said, "Well, boys, we've been scooped." They had, by accident, by stubbornness, by pigeon droppings, Penzias and Wilson had discovered the cosmic microwave background. It is worth pausing here to appreciate the sheer improbability of this moment. Two radio engineers, working for a telephone company, using equipment designed for satellite communications, had stumbled upon the single most important piece of evidence for the origin of the universe. They were not looking for it. They did not expect it. They spent months trying to make it go away. And meanwhile, just down the road, a team of brilliant theoretical physicists was frantically building the very instrument that would have detected the signal first, if only they had been a few months faster. The universe, it seems, has a sense of dramatic timing. Dicke himself bore the disappointment with grace. He and his team pivoted quickly, recognizing that confirming and extending the measurement was more important than who got there first. Peebles would go on to become one of the most influential cosmologists of the 20th and 21st centuries, eventually winning the Nobel Prize in Physics in 2019 for his theoretical contributions to our understanding of the universe's evolution. Wilkinson would devote his career to increasingly precise measurements of the CMB, his work ultimately leading to the satellite that bears his name. Two papers were published simultaneously in the astrophysical journal Letters In 1965, Penzias and Wilson's paper was modest in tone, simply reporting their measurement of excess antenna temperature. It ran barely 4 pages. The authors made no grand claims about the origin of the universe. They simply presented the data and noted that the excess temperature they measured was consistent with the prediction of Dick, Peebles, Roll, and Wilkinson. The Princeton group's paper, published alongside it, provided the cosmological interpretation. This was the relic radiation predicted by Big Bang theory, the afterglow of creation. The impact was seismic. The steady-state theory, which had no mechanism to produce such a uniform, omnidirectional microwave signal, was dealt a blow from which it never recovered. The Big Bang model was confirmed. The universe had a beginning, and that beginning had left a mark that could be measured with a radio antenna in New Jersey. In the years that followed, astronomers around the world scrambled to confirm and extend the measurement. Observations at different wavelengths were essential. If the signal was truly a blackbody remnant of the Big Bang, it should have a very specific spectrum, with a peak at a wavelength determined by its temperature, and a shape that precisely followed the mathematical curve derived by Max Planck at the dawn of quantum mechanics. Ground-based and balloon-borne measurements at various microwave and far-infrared frequencies gradually built up a picture of the spectrum, and it was broadly consistent with a blackbody, but the measurements were imprecise, contaminated by atmospheric absorption, and limited in wavelength coverage. The definitive test would require going to space. In 1978, Penzias and Wilson received the Nobel Prize in Physics for their discovery. Dick and his team, who had provided the theoretical framework, were not included. This omission remains one of the more debated decisions in Nobel history. And Alpher and Herman, who had predicted the radiation 30 years earlier, received no recognition at all from the Nobel Committee. Alpher, in particular, spent much of the rest of his life expressing frustration that his pioneering work had been overlooked. He passed away in 2007, never having received the prize that many felt he deserved. But the discovery itself was undeniable, and it opened a door to an entirely new way of studying the universe. Because the cosmic microwave background is not just a featureless glow. It is not merely a confirmation of the Big Bang. It is, as physicists would gradually come to realize over the following decades, the richest, most information-dense signal in all of astronomy. It is a cosmic Rosetta Stone, and learning to read it would transform cosmology from a speculative philosophy into a precision science. But first, we need to understand what, exactly, we are looking at when we observe the CMB. And one of the first and most remarkable things about it is its spectrum. When Penzias and Wilson made their discovery, they measured the CMB at a single wavelength, 7.35 centimeters. They found a temperature of about 3.5 Kelvin, but the theoretical prediction was more specific than just a temperature. Alpher and Herman, and later Dick and Peebles, had predicted that the CMB should have a very particular kind of spectrum, a blackbody spectrum. A blackbody is a physics term for an idealized object that absorbs all incoming radiation and emits radiation in a pattern that depends solely on its temperature. The Sun is approximately a blackbody. a hot piece of iron glowing in a forge, is approximately a blackbody. The important thing is that the spectrum of a blackbody, the curve that describes how much energy is emitted at each wavelength, has a specific and mathematically precise shape. It rises steeply at short wavelengths, peaks at a characteristic wavelength determined by the temperature, and then gradually falls off at longer wavelengths. The prediction was that the CMB should be a nearly perfect blackbody, because the early universe was in an exquisite state of thermal equilibrium. The photons and matter were so thoroughly mixed, so completely interacting, that they had reached a state of perfect balance. And when the photons were released at recombination, they carried the imprint of that equilibrium with them. But measuring the full spectrum of the CMB turned out to be extremely difficult from the ground. Earth's atmosphere absorbs microwaves at many wavelengths, making it impossible to see the full picture from the surface. Balloon-borne experiments in the 1970s and 80s made progress, but the measurements were noisy and incomplete. And then, in the late 1980s, a Japanese-American team led by Andrew Lange and Paul Richards even reported that the CMB spectrum deviated from a perfect blackbody, a finding that, if confirmed, would have upended our understanding of the early universe. It was against this backdrop of uncertainty that NASA launched the Cosmic Background Explorer satellite, known as COBE, on November 18, 1989. COBE was a triumph of persistence and ingenuity. The project had been conceived in the mid-1970s, when a group of young scientists, John Mather chief among them, responded to a NASA call for proposals with an ambitious plan to measure the CMB from orbit. The proposal was accepted, but the road to launch was long and grueling. Bureaucratic delays, technical hurdles, and budget battles consumed more than a decade. And then, on January 28, 1986, the Space Shuttle Challenger exploded 73 seconds after launch, killing all 7 crew members and grounding the shuttle fleet. COBE had been designed to fly on the shuttle. The disaster forced the team to completely redesign the satellite to fit on a smaller Delta rocket launched from Vandenberg Air Force Base in California. It was a crushing setback that added years to the timeline, but the team adapted, redesigned, rebuilt, and persevered. COBE carried 3 instruments, but the one that would settle the spectrum question was called FIRAS, the Far Infrared Absolute Spectrophotometer. Its principal investigator was John Mather himself, the quiet, methodical physicist who had been the heart and soul of the COBE project since its inception. Mather had first become interested in the CMB spectrum as a graduate student at Berkeley in the early 1970s. His doctoral thesis had been an attempt to measure the spectrum using a balloon-borne instrument, an effort that was ultimately thwarted by technical difficulties. But the experience had given him an intimate understanding of the challenges involved, and he carried that hard-won knowledge into the satellite mission. The results came quickly. Within 9 minutes of COBE reaching orbit, FIRAS returned its first spectrum. And when John Mather presented that spectrum at a meeting of the American Astronomical Society in January of 1990, the audience gave him a standing ovation. It was an extraordinary moment. Mather showed a single slide, the theoretical blackbody curve at 2.725 Kelvin, and overlaid on it the FIRAS data points. The data points fell exactly on the curve. You could not see the error bars. They were smaller than the thickness of the line. There was a moment of stunned silence in the audience, and then the applause erupted. Physicists do not typically give standing ovations at conferences, but this was not a typical result. This was proof that the universe was exactly what the Big Bang model predicted. A hot, dense plasma in perfect thermal equilibrium, whose radiation had been cooling and redshifting for over 13 billion years. The standing ovation was for the data, and for the decades of painstaking work that had led to its collection. Because the CMB spectrum measured by FIRAS was a perfect blackbody, not approximately perfect, not roughly consistent, perfect, the data points fell on the theoretical curve with a precision of better than 1 part in 10,000. No deviation, no anomaly, no surprises, just a flawless blackbody at a temperature of 2.725 Kelvin. It was the most perfect blackbody spectrum ever measured in nature, more precise than any laboratory experiment could produce. Nothing in the universe, not the sun, not a furnace, not any engineered device, radiates as perfectly as the cosmic microwave background. This was a triumph on multiple levels. It confirmed that the early universe was in thermal equilibrium, which is what you would expect from a hot, dense Big Bang. It ruled out a host of alternative cosmological models that predicted distortions in the spectrum, and it established, beyond any reasonable doubt, that the CMB was exactly what the theorists had predicted. The cooled remnant of the primordial fireball, redshifted by a factor of about 1,089 from its original temperature of roughly 3,000 Kelvin down to its present 2.725. The universe had handed us a near-perfect signal. And now the question became, what could we do with it? Because embedded in that seemingly featureless glow, invisible to Penzias and Wilson's crude antenna, invisible even to FIRAS, were tiny, almost impossibly faint variations in temperature, ripples, wrinkles, imperfections in the otherwise uniform fabric of the primordial light. And those imperfections are everything. To understand why, consider the universe we live in today. Look up at the night sky, and you see structure everywhere. Stars clustered into galaxies. Galaxies gathered into groups and clusters. Clusters strung together in filaments and walls and sheets, separated by vast, empty voids. The universe is lumpy. It is organized. It has architecture. But the CMB, when you first look at it, appears perfectly smooth. The same temperature in every direction to extraordinary precision. 2.725 Kelvin here. 2.725 Kelvin there. Everywhere you look, the same. And this presents a profound puzzle. If the universe started out perfectly smooth, perfectly uniform, with no variations in density whatsoever, then there would be nothing for gravity to grab onto, no seed for a star, no foundation for a galaxy. The universe would have expanded into an ever-thinning, ever-cooling soup of gas, utterly featureless forever. No stars, no planets, no chemistry, no life, just an infinite, darkening void. Obviously, that did not happen. So something must have broken the symmetry. There must have been variations in the early universe, regions that were ever so slightly denser than average, and regions that were ever so slightly less dense. The denser regions would have pulled in more matter through gravity, growing larger and denser over time, eventually collapsing into the galaxies and clusters we see today. The less dense regions would have been drained of matter, becoming the vast cosmic voids. If this picture is correct, then those density variations should be imprinted on the CMB. Regions that were slightly denser at the time of recombination would appear slightly hotter. Regions that were slightly less dense would appear slightly cooler. The differences would be minuscule, perhaps 1 part in 100,000 compared to the average temperature, but they should be there. And finding them was the mission of the second instrument aboard the COBE satellite, the Differential Microwave Radiometer, or DMR. Its principal investigator was a physicist named George Smoot, who had been searching for these tiny temperature fluctuations since the mid-1970s. Smoot was a restless, ambitious experimentalist. He had earned his doctorate at MIT studying particle physics, specifically the decay of exotic particles called kaons. But he was drawn to cosmology, to the grand questions about the origin of the universe, and he saw the CMB as the key to answering them. He began his search using instruments mounted on high-altitude aircraft, flying them above much of the Earth's atmosphere to reduce interference. The results were tantalizing, but not definitive. He knew that a satellite, free from atmospheric contamination entirely, was the only way to get a clear answer. The DMR instrument on COBE was designed to measure temperature differences between different parts of the sky, with a sensitivity of about 30 millionths of a degree. It observed the sky at 3 different frequencies to help distinguish the CMB signal from contaminating emissions produced by our own galaxy. And it worked. After more than 2 years of observation and meticulous analysis, the COBE team was ready to make its announcement. On April 23, 1992, at a meeting of the American Physical Society in Washington, D.C., Smoot presented the results. COBE had found the fluctuations, tiny variations in the temperature of the CMB, at the level of about 1 part in 100,000, exactly as theorists had predicted. The map was blurry. COBE's angular resolution was limited to about 7 degrees on the sky, meaning it could only see the broadest features of the temperature landscape. But the signal was unmistakable. The universe was not perfectly smooth at the time of recombination. It had structure. It had seeds. The COBE fluctuation map was displayed as an oval projection of the full sky, painted in splotches of blue and red, blue for slightly cooler than average, red for slightly warmer. The dominant feature was a large dipole pattern, one half of the sky slightly warmer than the other, caused by the Earth's motion through the CMB rest frame. Once that was subtracted, and the emission from our own galaxy removed, what remained was a mottled, apparently random pattern of hot and cold spots. To the casual viewer, it might have looked like noise. To a cosmologist, it was the face of creation. Those spots were the seeds of everything, the embryonic density fluctuations that would grow over billions of years, under the relentless pull of gravity, into the galaxies, galaxy clusters, and cosmic web we observe today. The reaction was electric. The discovery made the front page of the New York Times. Smoot himself, caught up in the excitement, described the fluctuations in a way that generated both headlines and controversy, comparing the CMB map to a glimpse of the fundamental structure of the universe itself. Stephen Hawking called it the most important discovery of the century, if not of all time. That was perhaps hyperbolic, but the significance was real. COBE had shown that the seeds of all cosmic structure, the precursors to every galaxy, every star, every planet, every living thing, were present in the universe when it was less than 400,000 years old, and they were visible, frozen in the oldest light in the cosmos. John Mather and George Smoot would share the Nobel Prize in Physics in 2006 for their work on COBE. The prize committee's citation noted that the COBE project could be regarded as the starting point for cosmology as a precision science. And precision was exactly what came next, because COBE's map, as groundbreaking as it was like looking at the world through frosted glass. You could see that there were objects out there, shapes and shadows, but you could not make out the details, and it was in the details that the real treasure lay. To understand why, we need to talk about sound waves, because the universe, in its infancy, was singing. In the first 380,000 years of cosmic history, before the CMB was released, the universe was a plasma, a tightly coupled fluid of photons, electrons, and atomic nuclei, all bound together by electromagnetic interactions. The photons could not travel freely, as we have discussed. They were constantly scattering off free electrons, but this tight coupling meant that the photons and the matter behaved as a single fluid, locked together in their motions. And in this fluid, sound waves could propagate. Here is how it worked. Imagine a region of the early universe that was slightly denser than its surroundings. This overdense region, pulled inward by its own gravity, began to compress. As it compressed, the density of photons within it increased, and so did the radiation pressure. That pressure pushed back against the gravitational collapse, causing the region to expand. But the expansion went too far, creating an underdense region, which then had too little pressure to resist gravity, and the process reversed. The region compressed again, and so on. This is an oscillation, a sound wave, just like the sound waves that travel through the air when you speak, or through the body of a guitar when you pluck a string. Except these sound waves were traveling through the photon-baryon plasma of the early universe at a speed of about half the speed of light. And they were cosmic in scale. These were not tiny vibrations. They were pressure waves rippling through the entire observable universe, compressing and rareifying matter and radiation on scales of hundreds of thousands of light years. Picture it, an ocean of light and matter filling the cosmos from edge to edge, oscillating, vibrating, ringing like a bell. Regions hundreds of thousands of light years across, pulsing in and out, compressed by gravity and blown apart by pressure, over and over again, for 380,000 years. The universe was a cosmic musical instrument, and it was playing a chord. Not a single note, but a complex, rich harmony of overtones, each one carrying information about the composition and geometry of the cosmos. And these oscillations left their mark on the CMB. Think about it this way. At the moment of recombination, when the photons were released, some of these oscillations were caught at the point of maximum compression. The regions were dense and hot, and the photons released from them had slightly higher energies, appearing as warm spots on the CMB sky. Other oscillations were caught at the point of maximum rarefaction. These regions were less dense and cooler, producing cold spots. Still, other oscillations were caught in between, partway through their cycle, producing intermediate temperatures. The result is a characteristic pattern of temperature fluctuations on the CMB sky, with a specific angular scale for each mode of oscillation. The longest sound wave, the one that had just enough time to compress once before recombination, produced the largest and most prominent feature. The next harmonic, which compressed and rarefied once, produced a smaller feature. The third harmonic, which went through 1.5 cycles, produced an even smaller feature. And so on, like the overtones of a musical instrument, when cosmologists plot the strength of the temperature fluctuations as a function of angular scale, they get what is known as the power spectrum of the CMB. And this power spectrum has a series of peaks and troughs, each one corresponding to a different harmonic of the primordial sound waves. The first peak, the tallest and most prominent, occurs at an angular scale of about 1 degree in the sky. This corresponds to the fundamental mode, the sound wave that had just enough time to compress once from the beginning of the universe to the moment of recombination. The location of this peak tells us something extraordinary. It tells us about the geometry of the universe. In a flat universe, where space is not curved, the fundamental sound wave subtends exactly about 1 degree on the sky. In a curved universe, the peak would shift to a different position. Observations have confirmed with stunning precision that the first peak is right where it should be for a flat universe. Our universe is geometrically flat, not curved like a sphere, not saddle-shaped like a hyperbolic surface. Flat. Euclidean geometry works on the largest scales imaginable. But the story does not end with the first peak, the second peak, the third peak, and the peaks beyond each carry their own information. The relative heights of the odd-numbered peaks compared to the even-numbered peaks tell us about the density of ordinary matter, the baryons, the protons, and neutrons that make up everything we can see and touch. A universe with more baryons has taller odd peaks relative to even peaks. The overall height of the peaks relative to the large-scale fluctuations tells us about the density of dark matter, the invisible substance that interacts with gravity but not with light. The way the peaks decrease in height at smaller angular scales, a process called damping, tells us about the thickness of the surface of last scattering, the finite duration of the recombination process. Every feature of the power spectrum, every peak, every trough, every subtle asymmetry, encodes a different piece of information about the composition, geometry, and history of the universe. Reading the CMB power spectrum is like reading the DNA of the cosmos. And the evidence for dark matter that emerges from this reading is particularly compelling. We cannot see dark matter. We cannot touch it, bottle it, or detect it directly in any laboratory. Yet the CMB tells us it is there, with a confidence that borders on mathematical certainty. Here is why. In the early universe, before recombination, ordinary baryonic matter was tightly coupled to the photons. When gravity compressed a region, the photons pushed back with radiation pressure, creating the acoustic oscillations we have described. But dark matter does not interact with photons. It does not feel radiation pressure. Dark matter simply falls into gravitational potential wells and stays there, accumulating. It acts as a gravitational anchor, deepening the wells into which the baryonic matter oscillates. This changes the pattern of the acoustic peaks in a very specific, predictable way. Without dark matter, the odd-numbered peaks and the even-numbered peaks would have approximately equal heights. But with dark matter deepening the gravitational wells, the compressions become more extreme than the rarefactions. The odd peaks, which correspond to maximum compression, are enhanced relative to the even peaks. The ratio of the heights of the first peak to the second peak is a direct measurement of the ratio of dark matter to baryonic matter in the universe, and the observed ratio matches a universe with about 5 times more dark matter than ordinary matter. 5 times. For every atom of hydrogen in the universe, there are 5 times as many particles of something else, something invisible, something that interacts only through gravity. And we can read that ratio directly from the music of the early universe, frozen into the peaks of the CMB power spectrum. But COBE could not read it. COBE's angular resolution was too coarse to see the individual peaks. It could see the broad outlines of the fluctuations, but not their detailed structure. To see the peaks, you needed better instruments, and they came. First, in a rush of ground-based and balloon-borne experiments in the late 1990s and early 2000s, the Boom-Ran-G experiment, flown on a balloon over Antarctica in 1998, was among the first to clearly detect the first acoustic peak, confirming the flatness of the universe. Boom-Ran-G, which stood for balloon observations of millimetric extragalactic radiation and geophysics, circled the Antarctic continent for 10.5 days, riding the polar vortex winds at an altitude of about 37 kilometers. The payload, dangling beneath a balloon the size of a football field, carried sensitive bolometric detectors cooled to 0.3 of a degree above absolute zero. When the team, led by Andrew Lange of Caltech and Paolo de Bernardis of the University of Rome, analyzed the data, they found a clear, unambiguous peak in the power spectrum at an angular scale of about 1 degree. The universe was flat. Euclidean geometry applied on the largest scales. It was a discovery that made headlines around the world. The Maxima experiment provided complementary measurements, also using a balloon platform, confirming the first peak and providing hints of the second. The Degree Angular Scale Interferometer, or DASI, operating from the South Pole, made a different kind of contribution entirely. In 2002, DASI announced the first detection of polarization in the CMB, a separate signal that provided independent confirmation of the acoustic oscillation picture, and opened an entirely new window onto the physics of the early universe. The polarization signal was faint, roughly 100 times weaker than the temperature anisotropy, but it was there, exactly as theory predicted. But the real revolution came from space. In June of 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, named in honor of David Wilkinson, the Princeton physicist who had been a driving force behind CMB research for decades, and who had passed away in 2002. Not long after the satellite he had helped design reached its orbit. Wilkinson had been one of Dick's original team at Princeton, the group that was scooped by Penzias and Wilson. He devoted his entire subsequent career to progressively more precise measurements of the CMB. And the satellite that bears his name was the culmination of that lifelong quest. WMAP was placed at the second Lagrange point of the Sun-Earth system, a gravitationally stable location about 1.5 million kilometers from Earth, where it could observe the sky without interference from our planet's heat or atmosphere. The satellite spun slowly, sweeping its two differential radiometers across the sky, comparing the temperatures of different directions, and gradually building up a full sky map. It is observed at 5 frequency bands, from 23 to 94 gigahertz, allowing the team to separate the CMB signal from contaminating foreground emissions. WMAP mapped the entire CMB sky with an angular resolution of about 13 arcminutes, roughly 50 times finer than COBE. The difference was like going from a thumbnail sketch to a detailed photograph. And when the WMAP team, led by Charles Bennett of Johns Hopkins University, released their first results in February 2003, the impact on cosmology was profound. The paper announcing the first-year results was one of the most cited scientific papers of the decade, and it established the precision cosmology that would define the field for the next 20 years. The WMAP power spectrum showed the first 3 acoustic peaks clearly resolved, along with the beginnings of additional peaks at smaller angular scales. By fitting theoretical models to this spectrum, the WMAP team was able to determine the fundamental parameters of cosmology with unprecedented precision. The age of the universe, 13.7 billion years, plus or minus about 200 million. The total density of matter and energy is consistent with a flat universe to within 2%. The composition, roughly 4.6% ordinary baryonic matter, roughly 23% dark matter, and roughly 72% dark energy. The mysterious force driving the accelerated expansion of the universe. These numbers defined what cosmologists call the concordance model, or more formally, the lambda CDM model. Lambda for the cosmological constant representing dark energy, CDM for cold dark matter. 6 parameters, 6 numbers that describe the large-scale properties of the entire observable universe. And WMAP determined nearly all of them. Think about what this means. 6 numbers. That is all it takes. With just 6 parameters, you can predict the full shape of the CMB power spectrum. Every peak, every trough, every damping tail. You can predict the age of the universe, its geometry, its composition, the rate at which it is expanding, and the amplitude and tilt of the primordial fluctuation spectrum. 6 numbers, and you have a working model of the cosmos. The first parameter is the density of ordinary baryonic matter, the protons, neutrons, and electrons that make up stars, planets, people, and everything you have ever touched or seen. It accounts for about 5% of the total energy budget. The second is the density of cold dark matter, the invisible substance that does not emit, absorb, or reflect light, but whose gravitational influence shapes the formation of galaxies and galaxy clusters. It accounts for about 27%. Together, ordinary matter and dark matter make up roughly a third of the universe's energy content. The remaining two-thirds is dark energy. The third parameter, the cosmological constant lambda, quantifies this mysterious component. Dark energy does not cluster. It does not dilute as the universe expands. It is a property of space itself, a constant energy density that fills every cubic centimeter of the cosmos and drives the acceleration of cosmic expansion. We do not know what it is. We have no satisfying theory to explain it. Its observed value is roughly 120 orders of magnitude smaller than the most naive theoretical estimates. A discrepancy so vast that it has been called the worst prediction in the history of physics, and yet there it is, accounting for 68% of everything. The fourth and fifth parameters describe the primordial fluctuations themselves, their overall amplitude, which determines how lumpy the universe was at its birth, and their spectral index, which describes how the amplitude varies with scale. A spectral index of exactly 1 would mean that fluctuations have the same amplitude at all scales, a prediction of the simplest models of inflation. The measured value is about 0.965, slightly less than 1, exactly the small departure that most inflationary models predict. This near unity, but not quite unity spectral index is one of the strongest pieces of evidence that inflation actually happened. The sixth parameter is the optical depth to reionization, which measures how much the CMB photons have been scattered by free electrons produced when the first stars and galaxies reionized the intergalactic medium. A few 100 million years after the Big Bang, this parameter connects the CMB to the epoch of first light, the moment when the first luminous objects turned on and began flooding the universe with ultraviolet radiation. 6 numbers, the entire observable universe, compressed into half a dozen parameters. But WMAP was not the end. Over 9 years of operations, from 2001 to 2010, WMAP continued to refine its measurements, releasing 5 major data sets, each more precise than the last. The final 9-year results, published in 2012, reduced the allowed volume of cosmological parameter space by a factor of 68,000 compared to pre-WMAP measurements. The universe was being measured with the precision of a Swiss watch. And then came Planck. The European Space Agency launched the Planck satellite on May 14, 2009. Like WMAP, it was stationed at the second Lagrange point. But Planck was a leap forward in every respect. It observed the sky in 9 frequency channels, from 30 gigahertz to 857 gigahertz, compared to WMAP-S5. It had finer angular resolution, greater sensitivity, and better control of systematic errors. Its instruments included both low-frequency receivers and high-frequency bolometers, the latter cooled to 1/10 of a degree above absolute zero to minimize instrument noise. Planck scanned the sky continuously from August 2009 to October 2013, and its data releases in 2013, 2015, and 2018 represent the definitive measurements of the CMB to date. The Planck power spectrum is a thing of beauty. 18 peaks and troughs in the temperature spectrum, 6 in the temperature polarization cross spectrum, 5 in the pure polarization spectrum, all matching the theoretical predictions of the lambda CDM model with jaw-dropping accuracy. 5 of the 6 fundamental cosmological parameters are determined to better than 1% precision. The age of the universe is measured to be 13.8 billion years. The Hubble constant, the rate at which the universe is currently expanding, is measured to be 67.4 kilometers per second per megaparsec. The universe is approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. The precision is almost surreal. Consider what Planck has accomplished. It has measured the age of the universe to within about 50 million years. The universe is 13.8 billion years old, and we know that to within less than half of 1%. It has measured the curvature of space to be flat to within 0.4% of the critical density. It has been determined that ordinary matter makes up 4.9% of the universe's energy content, with an uncertainty of less than 0.2%. These are measurements of the entire observable universe, a sphere roughly 93 billion light-years across, and we are pinning down its properties with the kind of precision that would have seemed like science fiction just 30 years ago. The Planck satellite itself was an engineering masterpiece. Its high-frequency instrument included bolometric detectors cooled to 1/10 of a degree above absolute zero, making them among the coldest objects in the universe at the time of operation. The cooling chain was a nested set of systems. Passive radiators exposed to deep space brought the temperature down to about 50 Kelvin. A hydrogen sorption cooler reduced it further to about 18 Kelvin. A mechanical Joule-Thomson cooler brought it to around 4 Kelvin. And finally, a dilution refrigerator, a device that exploits the quantum properties of helium-3 and helium-4 mixtures, pushed the temperature to its final value of 0.1 Kelvin. All of this operating autonomously, 1.5 million kilometers from Earth for over 4 years. But the Planck data do more than just confirm what WMAP found. They probe the physics of the early universe at a level of detail that was unimaginable a generation ago. They constrain the number of neutrino species in the universe. They set limits on the mass of neutrinos. They test the predictions of Big Bang nucleosynthesis by independently measuring the density of baryons. They search for subtle deviations from the standard model, including non-Gaussianity in the primordial fluctuations, departures from a perfect power law spectrum, and contributions from gravitational waves generated during the earliest moments of the universe. And it is here that the CMB connects to one of the deepest and most tantalizing ideas in all of physics: cosmic inflation. The theory of inflation was born out of frustration. By the late 1970s, the Big Bang model was well established, but it had several nagging problems that it could not explain. The first was the horizon problem. The CMB, as we have noted, is extraordinarily uniform, the same temperature in every direction to 1 part in 100,000. But here is the puzzle. When we look in one direction in the sky, we are seeing CMB photons that were released from a region of space that is now about 46 billion light-years away in that direction. When we look in the exact opposite direction, we see photons from a region 46 billion light-years away in the other direction. These two regions are separated by 92 billion light-years, and in the standard Big Bang model, they were never in causal contact. They were too far apart for light or any signal to have traveled between them in the age of the universe. At the time, the CMB was emitted. So how did they end up at the same temperature? How did they know to be so precisely uniform? It is as if you walked into a room and found that the air temperature was exactly the same in every corner, down to the thousandth of a degree. But you also knew that no air conditioning system had ever operated in the building, and that the room was so large that heat could not possibly have traveled from one side to the other. The uniformity would seem miraculous. It would demand an explanation. And in the standard Big Bang model without inflation, no explanation existed. The uniformity of the CMB was a brute fact, unexplained, seemingly requiring impossibly precise initial conditions. The second problem was the flatness problem. General relativity tells us that the geometry of the universe, whether it is flat, curved positively like a sphere, or curved negatively like a saddle, depends on its total energy density. If the density is exactly equal to a specific critical value, the universe is flat. If it is slightly more, the universe is a sphere. Slightly less, a saddle. The trouble is that any deviation from perfect flatness grows over time. A universe that starts out very slightly curved will become more and more curved as it expands. To be as flat as we observe it to be today, the universe would have had to be flat to an almost absurd degree of precision at the very beginning, within 1 part in 10 to the 60th power. That is a 1 followed by 60 zeros. To put that in perspective, it is like balancing a pencil on its tip so precisely that it stands upright not for a second, not for a minute, but for 14 billion years. It is like setting the initial conditions of the universe with a precision that exceeds the number of atoms in the observable universe. This seemed like an incredible fine-tuning, as if the universe had been set up with impossibly precise initial conditions. And fine-tuning in physics is usually a sign that you are missing something, that there is a deeper explanation you have not found yet. In December of 1979, a young physicist named Alan Guth, then a postdoc at Cornell University, had an insight that would eventually address both of these problems. Guth was not, at the time, a cosmologist. He was a particle physicist, and he had been thinking about a completely different problem: the overproduction of magnetic monopoles in certain grand, unified theories of particle physics. These theories predicted that the early universe should have been littered with exotic particles called magnetic monopoles, particles that carry a single magnetic pole, north or south, rather than the paired north-south poles of every known magnet. And yet, no magnetic monopole has ever been observed. Where did they all go? Guth realized that a period of extraordinarily rapid exponential expansion in the very early universe could solve the monopole problem by diluting these exotic particles to undetectable densities. But as he worked through the implications, he discovered something far more profound. This same rapid expansion could solve the horizon problem and the flatness problem as well. In a now famous notebook entry dated December 7th, 1979, Guth wrote in capital letters, "Spectacular realization." Guth proposed that in the very first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion. In this period, lasting perhaps from 10 to the negative 36th seconds to 10 to the negative 32nd seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th. In less than a billionth of a trillionth of a second, a region smaller than a proton was inflated to a size larger than the entire observable universe today. The numbers are staggering. The expansion happened faster than the speed of light, which is permitted in general relativity because it was space itself that was expanding, not objects moving through space. This is cosmic inflation, and like many great ideas, it was quickly improved upon by others. Guth's original model had a technical flaw. It ended inflation too abruptly, producing a universe full of bubble walls and inhomogeneities. Within a few years, Andrei Linde in the Soviet Union, and independently, Andreas Albrecht and Paul Steinhardt in the United States developed improved versions called new inflation and chaotic inflation that avoided these problems. Today, there are dozens of inflationary models, each with slightly different predictions, but they all share the core idea of a brief, violent exponential expansion in the earliest moments of the cosmos. This is cosmic inflation. Inflation solves the horizon problem elegantly. Before inflation, the entire observable universe was contained within a tiny region, small enough for light to traverse many times over. Everything was in causal contact. Everything could reach thermal equilibrium. Then inflation stretched this tiny, uniform region to cosmic proportions. The uniformity was baked in before the expansion, and inflation preserved it. Inflation solves the flatness problem too. Just as inflating a balloon stretches its surface until any small patch looks flat, inflation stretches the geometry of the universe until it becomes indistinguishable from flat, regardless of what its curvature was before. The fine-tuning is not required. Flatness is a natural outcome of inflation, not a special initial condition. But inflation does something even more extraordinary. Quantum mechanics tells us that even the emptiest vacuum is not truly empty. It seethes with tiny, random fluctuations in energy and density. Virtual particles popping in and out of existence on unimaginably small scales. During inflation, these quantum fluctuations were stretched to macroscopic, then to cosmic scales. They became the seeds, the initial density variations that would later grow under the influence of gravity into the galaxies and galaxy clusters we observe today. In other words, inflation provides a mechanism for generating the very fluctuations we see in the CMB, the wrinkles in time that COBE discovered, the acoustic peaks that WMAP and Planck mapped in exquisite detail. All trace back to quantum fluctuations amplified by inflation. The largest structures in the universe, galaxy superclusters spanning hundreds of millions of light years, began as submicroscopic quantum noise in the first trillionth of a trillionth of a trillionth of a second. This is, to put it mildly, an astonishing claim, and it demands extraordinary evidence. And that evidence comes in the form of light itself. Not the temperature of the light, not the intensity of the light, but the way the light vibrates, its polarization. If you have ever worn a pair of polarized sunglasses, you have experienced polarization in action. Ordinary sunlight vibrates in all directions at once. It oscillates up and down, side to side, and at every angle in between, all simultaneously. A polarizing filter strips away most of those vibrations, allowing only light oscillating in one particular direction to pass through. That is why polarized sunglasses reduce glare. They block the horizontally polarized light bouncing off roads and water surfaces, letting through only the vertically polarized component. The cosmic microwave background is also polarized. Not strongly. About 10% of the CMB light carries a net polarization, a subtle preference for vibrating in one direction over another. But that faint signal carries a staggering amount of information that cannot be extracted from temperature measurements alone. The polarization of the CMB arises from a process called Thomson scattering. In the hot plasma of the early universe, before recombination, photons were constantly bouncing off free electrons. When a photon scatters off an electron, the polarization of the outgoing photon depends on the direction of the incoming light. If light is coming in from all directions equally, the polarizations cancel out, and the scattered light is unpolarized. But if there is an imbalance, if there is more light coming from some directions than others, the cancellation is incomplete, and the scattered photon carries a net polarization. This is exactly what happens near the surface of last scattering. As recombination proceeds, the photons are being released from the plasma, and the temperature fluctuations, those hot and cold spots we have been discussing, create a quadrupole pattern in the radiation field. Light arrives at each electron with slightly different intensities from different directions. The Thomson scattering then converts this intensity difference into a polarization signal, imprinted on the CMB photons at the moment of their liberation. The polarization pattern on the sky can be decomposed into two distinct types. Much like a vector field can be split into a curl-free component and a divergence-free component. Physicists call these two types E modes and B modes, named by analogy with the electric and magnetic fields in electromagnetism. E mode polarization has a specific geometric property. If you imagine the polarization direction at each point on the sky as a short line segment, then E-mode patterns are either radial, pointing toward or away from a central point, or tangential, wrapping around a central point in concentric circles. The key feature is that this pattern has no handedness. If you look at it in a mirror, it looks the same. E-modes are produced by ordinary density fluctuations, the same compressions and rarefactions that create the acoustic peaks in the temperature spectrum. B-mode polarization is different. B-mode patterns have a swirling, pinwheel quality to them. If you look at a B-mode pattern in a mirror, it looks like it is spinning in the opposite direction. It has a handedness, a chirality that E-modes lack. And this is crucial because ordinary density perturbations, the simple compressions and rarefactions of the primordial plasma, cannot produce B-modes. They can only produce E-modes. So what can produce B-modes? Two things. The first is gravitational lensing. As CMB photons travel across the universe for billions of years, they pass through regions of concentrated mass, galaxy clusters, dark matter halos, the large-scale filamentary structure of the cosmic web. The gravity of these structures bends the paths of the photons, distorting the CMB map in subtle but measurable ways. This gravitational lensing takes some of the E-mode polarization and converts it into B-mode polarization. The effect is small, but it has been detected, first by the South Pole Telescope in collaboration with the Herschel Space Observatory in 2013, and subsequently confirmed by numerous other experiments. The second source of B-modes is far more exciting. Gravitational waves. Not the gravitational waves detected by LIGO and Virgo from colliding black holes and neutron stars. Those are produced by astrophysical events in the relatively recent universe. The gravitational waves that cosmologists are hunting in the CMB are primordial. They were generated during inflation itself, in the first inconceivably tiny fraction of a second after the Big Bang, when the universe underwent its explosive expansion. Inflation theory predicts that quantum fluctuations in the gravitational field were amplified to cosmic scales, producing a background of gravitational waves that rippled through the primordial plasma. These primordial gravitational waves would have stretched and squeezed the plasma in a specific way, creating the kind of quadrupole anisotropy that Thomson's scattering converts into polarization. But because gravitational waves stretch space itself, not just the matter within it, they produce a polarization pattern with that distinctive swirling, handed quality. They produce B-modes. The amplitude of the primordial B-mode signal depends on the energy scale of inflation. The higher the energy at which inflation occurred, the stronger the gravitational waves it produced, and the larger the B-mode signal. Physicists parameterize this with a quantity called the tensor-to-scalar ratio, denoted by the letter R. Current observations from the BICEP/Keck collaboration combined with Planck data constrain R to be less than about 0.036, meaning that if inflationary gravitational waves exist, they are at least that faint. Some models of inflation predict values of R that are within reach of the next generation of experiments. Others predict values so small that they may never be detectable. The stakes could not be higher. A detection of primordial B-modes would confirm inflation, pin down the energy scale at which it occurred, and provide a direct observational window into physics at energies 1 trillion times higher than anything achievable by the Large Hadron Collider at CERN. A null result, on the other hand, would rule out large classes of inflationary models and force theorists to confront the possibility that inflation, if it happened, was far more subtle than currently imagined. If primordial B-modes could be detected, it would be the smoking gun for inflation. It would confirm that the universe underwent a period of exponential expansion in its earliest moments. It would tell us about the energy scale at which inflation occurred, which in turn would reveal information about physics at energies far beyond the reach of any particle accelerator ever built or conceivable. It would be, in the words of many cosmologists, one of the greatest discoveries in the history of science. And in March of 2014, a team of scientists announced that they had found it. The BICEP telescope was a compact, purpose-built instrument stationed at the Amundsen Scott South Pole Station in Antarctica. The South Pole is one of the best locations on Earth for microwave observations. The air there is extraordinarily dry and cold, which minimizes the amount of atmospheric water vapor that can absorb and emit microwaves, contaminating the CMB signal. The atmosphere above the pole is also remarkably stable, allowing for long, uninterrupted observations. Bise-Petwo had been staring at a single patch of sky, roughly 1 to 2% of the full sky, for 3 years, from 2010 to 2012. This patch had been chosen because it appeared to be relatively free of contaminating emission from the Milky Way galaxy, particularly from the tiny grains of interstellar dust that permeate our galaxy and emit polarized microwave radiation of their own. The telescope was sensitive to a single frequency, 150 gigahertz, and it was equipped with an array of superconducting detectors cooled to a fraction of a degree above absolute zero. On March 17, 2014, the Bise-Petwo team, led by John Kovac of the Harvard-Smithsonian Center for Astrophysics, held a press conference at the Center for Astrophysics in Cambridge, Massachusetts. They announced that Bise-Petwo had detected B-mode polarization in the CMB at a level corresponding to a tensor-to-scalar ratio of roughly 0.2. The tensor-to-scalar ratio, denoted by the letter R, is the key parameter that describes the amplitude of primordial gravitational waves relative to the density perturbations. A value of R equal to 0.2 would indicate surprisingly powerful gravitational waves from inflation, implying that inflation occurred at an extremely high energy scale. The announcement was electrifying. Media coverage was extensive and euphoric. Physicists spoke openly about Nobel Prizes. Andre Linde, one of the founders of inflationary theory, was famously filmed reacting to the news in real time, visibly moved to tears at his doorstep as a colleague arrived to tell him the result. The video went viral, but almost immediately, doubts began to surface. The concern centered on dust. Interstellar dust grains in the Milky Way are not randomly oriented. They tend to align with the galaxy's magnetic field. And when they emit microwave radiation, that radiation is polarized. Critically, the polarization pattern from dust can mimic the B-mode signal from primordial gravitational waves. To claim a detection of primordial B-modes, you have to be absolutely certain that your signal is not contaminated by dust. The Bise-Petwo team had tried to account for dust. They used several models to estimate the expected dust contribution in their patch of sky, and they argued that the dust signal was much smaller than the signal they observed. But there was a problem. The best data on dust polarization came from the Planck satellite, and at the time of the Bise-Petwo announcement, Planck's dust maps had not yet been publicly released. The Bise-Petwo team had used preliminary, indirect estimates of the dust contribution, and some of those estimates were based on a Planck presentation slide that, as it turned out, was not directly comparable to the quantity they needed. Over the following months, the excitement slowly curdled into uncertainty. At a conference of the American Astronomical Society in June 2014, astronomer David Spergel presented arguments that the Bise-Petwo signal could be explained by dust. The Bise-Petwo team revised their paper, adding an appendix that acknowledged the dust uncertainty more fully. And then, in September 2014, the Planck collaboration released its own analysis of dust polarization in the Bice-Petewo sky patch. The Planck data showed that the polarized emission from dust in the Bice-Petewo region was far stronger than the Bice-Petewo team had assumed. The dust signal was comparable to, and potentially as large as, the entire signal that Bice-Petewo had attributed to primordial gravitational waves. The final blow came on January 30, 2015, when a joint analysis of Bice-Petewo and Planck data was published. The two teams had combined their data sets, overlaying the Bice-Petewo measurements at 150 GHz with Planck measurements at 353 GHz, a frequency at which virtually all the polarized signal comes from dust. The match was devastating. The regions where Bice-Petewo saw its strongest signal were the same regions where Planck saw the strongest dust emission. The conclusion was inescapable. The detected signal could be entirely attributed to dust in the Milky Way. The detection of primordial gravitational waves was officially dead. It was a painful episode for the scientific community. The premature announcement, the media frenzy, the hopes raised and then dashed. But it was also, in a broader sense, science working as it should. A result was claimed, scrutinized, tested against independent data, and ultimately shown to be incorrect. No careers were destroyed. No reputations were permanently tarnished. The BICEP program continued, building more sensitive instruments, adding frequency channels to better separate the primordial signal from dust. The lesson was absorbed. The detection of primordial B modes, if they exist, will require extraordinary care, multiple frequencies, exquisite control of systematic errors, and patience. And the search goes on, because the question that Bice-Petewo tried to answer, whether inflation produced detectable gravitational waves, remains one of the most important open questions in all of physics. But polarization is not the only way that the CMB continues to yield secrets about the universe. The ancient photons of the cosmic microwave background do not travel through empty space on their journey to our detectors. They pass through the universe. And the universe, as it turns out, is not empty at all. Between the surface of last scattering and our telescopes lies the entire cosmic web: galaxies, galaxy clusters, filaments of dark matter stretching across hundreds of millions of light years, vast empty voids, and everywhere the invisible scaffolding of dark matter holding it all together. And as the CMB photons pass through this web, the web leaves its mark on them. One of the most important of these secondary effects was predicted in 1969 by two Soviet physicists, Rashid Sunyaev and Yakov Zeldovich. Both were protégés of the legendary Yakov Borisovich Zeldovich, one of the greatest theoretical physicists of the 20th century, a man who made fundamental contributions to nuclear physics, astrophysics, and cosmology while working, for much of his career, in the classified Soviet nuclear weapons program. Sunyaev, born in 1943 in Tashkent, was a young and brilliant student who began working with Zeldovich while still in his 20s. Together, they predicted a remarkable phenomenon. When CMB photons pass through a galaxy cluster, they encounter an immense cloud of superheated gas, the intracluster medium, a plasma with temperatures reaching tens of millions of degrees. The electrons in this plasma are moving at enormous speeds, carrying tremendous amounts of kinetic energy. When a low-energy CMB photon collides with one of these energetic electrons, it receives a boost. The electron transfers some of its energy to the photon, kicking it up to a higher frequency. This is called inverse Compton scattering, because the photon gains energy from the electron rather than the other way around. The result is a characteristic distortion of the CMB spectrum in the direction of a galaxy cluster. At low microwave frequencies, the CMB appears slightly dimmer than average because photons have been scattered out of those frequencies. At high frequencies, it appears slightly brighter because those photons have been boosted to higher energies. The transition point, the frequency at which the effect switches from a decrement to an increment, occurs at approximately 217 gigahertz. This is the thermal Sunyaev-Zeldovich effect, and it has a remarkable property that makes it uniquely powerful for cosmology. The strength of the effect does not depend on the distance to the galaxy cluster. A cluster at a redshift of 0.1, relatively nearby in cosmic terms, produces the same distortion as an identical cluster at a redshift of 2, deep in the distant universe. This is because the CMB photons are everywhere, filling all of space uniformly. No matter how far away the cluster is, there are always CMB photons passing through it, getting scattered, getting boosted. This distance independence means that the Sunyaev-Zeldovich effect can be used to find galaxy clusters at any redshift, even in the very distant universe, where clusters are too faint to see with optical or X-ray telescopes. It is one of the few techniques in astronomy that does not suffer from cosmological dimming, the tendency for more distant objects to appear fainter. A galaxy at the edge of the observable universe produces the same SZ signal as an identical galaxy next door. This makes the SZ effect a uniquely powerful tool for probing the distant universe. The South Pole Telescope has used this technique to discover well over 1,000 galaxy clusters, many of them previously unknown, simply by looking for the characteristic dimming of the CMB at microwave frequencies. The Atacama Cosmology Telescope has compiled its own extensive catalog, and the Planck satellite, with its all-sky coverage, has produced a catalog of over 1,000 SZ-detected clusters spanning a wide range of redshifts. These cluster catalogs are not just astronomical curiosities. They are powerful tools for cosmology, because the number of massive galaxy clusters at different epochs of cosmic history depends sensitively on the total amount of matter in the universe, the properties of dark energy, and the growth rate of cosmic structure. Counting clusters and tracking how their numbers evolve over time provides an independent check on the cosmological parameters derived from the CMB power spectrum itself. And when those checks agree, which they largely do, our confidence in the standard model of cosmology grows stronger. There is also a second, more subtle version of the effect, called the kinematic Sunyaev-Zeldovich effect. This occurs when a galaxy cluster is moving with respect to the CMB rest frame, which essentially all clusters are, since they have peculiar velocities driven by the gravitational pull of surrounding large-scale structure. The bulk motion of the cluster gives the scattered photons an additional Doppler shift. Unlike the thermal effect, which has a characteristic frequency dependence. The kinematic effect simply raises or lowers the apparent CMB temperature without changing the shape of the spectrum. If the cluster is moving toward us, the CMB appears slightly warmer in that direction. If it is moving away, slightly cooler. The kinematic Sunyaev-Zeldovich effect has been much harder to detect because it is typically an order of magnitude weaker than the thermal effect, but it has been measured statistically, and it offers a direct way to probe the velocities of galaxy clusters, mapping the flows of matter on the largest scales, and testing our models of how structure grows under the influence of gravity. But galaxy clusters are not the only structures that leave their mark on the CMB. The photons are also deflected by the gravity of everything they encounter along the way, and this gravitational lensing of the CMB has become one of the most productive areas of modern observational cosmology. Imagine a perfectly smooth sheet of glass, and behind it, a detailed image. Now imagine that the glass is not perfectly smooth. It has gentle undulations, slight variations in thickness, like an old window pane. The image behind the glass will be distorted. Straight lines will bend, patterns will be stretched or compressed. The features of the image will be shifted slightly from their true positions. This is what gravitational lensing does to the CMB. The dark matter and ordinary matter distributed throughout the universe between us and the surface of last scattering acts like that warped pane of glass. The hot and cold spots of the CMB are shifted, magnified, or demagnified as the photons pass through regions of different gravitational potential. The statistical properties of the CMB map are altered in predictable ways. By carefully measuring these distortions, cosmologists can reconstruct a map of the total matter distribution between us and the CMB. Not just the visible matter, the galaxies and gas clouds, but all the matter, including dark matter, which makes up about 85% of the total. The Atacama Cosmology Telescope collaboration, using data collected from the high Chilean desert, produced in 2023 the most detailed dark matter map ever constructed from CMB lensing. Covering a full quarter of the sky, the map shows the cosmic web in exquisite detail, the filaments and clusters and voids that define the large-scale architecture of the universe. CMB lensing is also sensitive to the total mass of neutrinos. Neutrinos, those ghostly, nearly massless particles that barely interact with anything, nevertheless have a measurable effect on cosmic structure. Because they move at nearly the speed of light, neutrinos tend to stream freely out of regions of gravitational concentration, smoothing out the matter distribution on small scales. The heavier the neutrinos, the more they are, and the more the lensing signal is suppressed at certain angular scales. By measuring the CMB lensing spectrum with sufficient precision, cosmologists can effectively weigh the neutrinos, setting limits on their total mass that are competitive with, and in some cases tighter than, the constraints from laboratory experiments. Planck's measurement of the lensing potential, extracted from the 4-point correlation function of the temperature and polarization maps, has already provided significant constraints, and the next generation of experiments, including the Simons Observatory and CMBS4, will push these constraints even further, potentially reaching the sensitivity needed to detect the minimum neutrino mass allowed by particle physics experiments, roughly 0.06 electron volts. This brings us to one of the most fascinating frontiers of CMB science: its connection to neutrino physics and the cosmic neutrino background. The cosmic neutrino background is the neutrino analog of the CMB, just as the cosmic microwave background is a relic of the moment when photons decoupled from matter. The cosmic neutrino background is a relic of an even earlier epoch, roughly 1 second after the Big Bang, when the universe cooled enough that neutrinos stopped interacting with the surrounding plasma. At that moment, the neutrinos began streaming freely through space, and they have been doing so ever since. Today, the cosmic neutrino background is predicted to have a temperature of roughly 1.95 Kelvin, slightly cooler than the CMB's 2.725 Kelvin. The reason for the temperature difference is that after the neutrinos decoupled, the remaining electrons and positrons in the plasma annihilated each other, producing photons and heating the photon bath slightly. The neutrinos, already decoupled, did not share in this heating. The ratio of the neutrino temperature to the photon temperature can be calculated precisely from the physics of the early universe, and it works out to the cube root of 4/11, or approximately 0.714. The cosmic neutrino background has never been directly detected. The neutrinos within it have energies of roughly 1/10,000th of an electron volt, trillions of times less energetic than the neutrinos detected from the sun or from nuclear reactors. Detecting them directly is a monumental challenge. One proposed experiment, called Ptolemy, aims to capture relic neutrinos on a target of tritium, a radioactive form of hydrogen. When a cosmic neutrino is absorbed by a tritium nucleus, it induces beta decay, producing a helium-3 nucleus and an electron. The electron would have a slightly higher energy than the electrons produced by normal beta decay. The excess corresponding to the neutrinos' rest mass energy, but the effect is so tiny and the rate so low that detecting it requires extraordinary precision, and even the most optimistic estimates suggest that direct detection remains years or decades away. But the cosmic neutrino background has been indirectly confirmed through the CMB. The presence of relic neutrinos affects the expansion rate of the early universe, which in turn affects the detailed shape of the CMB power spectrum. The number of neutrino species is parameterized by a quantity called the effective number of relativistic species, conventionally denoted as N-effective. The standard model of particle physics predicts 3 species of neutrinos, and when the subtle effects of incomplete decoupling are accounted for, the predicted value of N-effective is 3.044. Planck's measurement of this quantity is 2.99, plus or minus 0.17, in extraordinary agreement with the prediction. In other words, the CMB has told us indirectly that the cosmic neutrino background exists, that it contains exactly 3 species of neutrinos, and that their temperature is almost exactly what Big Bang theory predicts. This is a remarkable achievement. Without ever detecting a single relic neutrino directly, we have confirmed their existence through their gravitational influence on the ancient light of the cosmos. But the CMB holds more surprises still, because alongside its precision confirmations of the standard model of cosmology, The CMB also contains anomalies, features that do not quite fit, unexplained details that nag at the edges of our understanding. The most famous of these is the cold spot. First detected in data from the WMAP satellite and later confirmed by Planck, the CMB cold spot is a region of unusually low temperature located in the southern hemisphere of the CMB sky, in the direction of the constellation Eridanus. It spans roughly 5 degrees in the sky, about 10 times the angular diameter of the full moon, and it is approximately 70 millionths of a degree cooler than the average CMB temperature. That may sound trivially small, but the cold spot is not anomalous because of its temperature alone. It is anomalous because of its size and its surroundings. The spot is unusually large for a cold region of that depth, and it is encircled by a ring of anomalously warm CMB, creating a contrast that appears in fewer than 1% of simulated CMB skies based on the standard cosmological model. What is causing the cold spot? The question has spawned a cottage industry of theoretical explanations, some mundane, some exotic. One leading hypothesis involves a supervoid, a vast underdense region of the universe between us and the surface of last scattering. When CMB photons pass through a large void, they experience what is called the integrated Sachs-Wolf effect. As the photons enter the void, they climb into a gravitational potential well, losing energy. Normally, they would regain that energy as they climb back out on the other side. But if the void is expanding, which it does due to dark energy, the potential well becomes shallower during the time the photons are inside it. The photons exit with less energy than they entered with, appearing slightly cooler. In 2015, astronomers using data from the PAN-SDARRS survey and other catalogs reported the detection of a large supervoid in the direction of the cold spot, centered about 3 billion light-years from Earth and stretching roughly 1.8 billion light-years across. The supervoid contains approximately 20 to 30% less matter than the surrounding cosmic average. In 2021, the Dark Energy Survey confirmed the existence of this Eridanus supervoid using gravitational lensing mass maps, finding it to be the most prominent large-scale underdensity in their entire dataset. But there is a catch. Calculations suggest that the integrated Sachs-Wolf effect from the known supervoid can explain at most about 20% of the cold spot's temperature depression. The void is large, but not large enough. Some researchers have argued that the standard model underestimates the effect, perhaps because dark energy is not behaving exactly as expected. Others have suggested that additional, smaller voids along the same line of sight might contribute, and some have proposed more exotic explanations, cosmic textures, which are topological defects left over from phase transitions in the early universe, or even the imprint of another universe that collided with ours before inflation separated us forever. As of now, the cold spot remains unexplained. It may simply be a rare statistical fluctuation, the kind of feature that you would expect to find in 1 out of every 100 random realizations of the universe. Or it may be a hint of something deeper, a crack in the standard model, a signal of new physics hiding in the oldest light. The cold spot is not the only anomaly. The CMB exhibits what has been called the axis of evil, an alignment of the largest scale temperature patterns with a particular direction in space, roughly aligned with the plane of the solar system's orbit around the Sun. This alignment, first noted in WMAP data and confirmed by Planck, is puzzling because the standard model predicts no preferred directions on the sky. There is also a hemispherical asymmetry, a slight but statistically significant difference in the amplitude of the fluctuations between the northern and southern halves of the CMB sky, and there is a curious deficit of power at the very largest angular scales, meaning that the broadest temperature fluctuations are slightly weaker than the model predicts. None of these anomalies individually is statistically overwhelming. Each one has a probability of a few percent or less of occurring by chance. But together, they create an uneasy feeling that there might be something we are missing, something about the universe or about our analysis that the standard 6-parameter model does not fully capture. Or perhaps they really are just statistical flukes. After all, when you look at as much data as Planck has provided, some features are bound to look unusual by chance. The question is whether future experiments with even greater sensitivity and sky coverage will strengthen these anomalies or wash them away. And speaking of what future experiments might reveal, there is one more thing the CMB can teach us, perhaps the most profound thing of all. The CMB is not just a snapshot of the infant universe. It is also a probe of the universe's ultimate fate. The accelerating expansion of the universe, driven by dark energy, was one of the most shocking discoveries in the history of science. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt of the Australian National University, and Adam Rees of Johns Hopkins University, announced that distant Type 1a supernovae were fainter than expected, implying that the expansion of the universe was speeding up rather than slowing down. The result was so unexpected that both teams initially suspected they had made an error. Perlmutter has recounted how his team spent months searching for systematic problems in their data, reluctant to believe what the observations were telling them. But the two teams, working independently with different telescopes, different analysis methods, and different supernova samples, arrived at the same conclusion. The expansion was accelerating. Something was pushing the universe apart. The discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. But the CMB had already been hinting at dark energy before the supernova teams found it. But the CMB had already been hinting at dark energy before the supernova teams found it. The location of the first acoustic peak in the CMB power spectrum tells us that the universe is geometrically flat, meaning its total energy density equals the critical density. Yet the total amount of matter, both ordinary and dark, accounts for only about 31% of the critical density. The remaining 69% must be something else, something that contributes to the energy budget of the universe without clustering like matter, something that drives the expansion to accelerate: dark energy. The CMB, combined with other observations, constrains dark energy to be consistent with a cosmological constant, a fixed energy density permeating all of space. But the nature of dark energy remains one of the deepest mysteries in physics. Is it truly constant, the same at all times and in all places? Or is it changing, evolving, perhaps growing stronger or weaker as the universe expands? Different models of dark energy predict subtly different effects on the growth of cosmic structure. Effects that can be probed through CMB lensing, the integrated Sachs-Wolf effect, and the Sunyaev-Zeldovich effect. Recent results from the Dark Energy Spectroscopic Instrument, which has been mapping the three-dimensional distribution of galaxies with unprecedented precision, have hinted that dark energy may not be perfectly constant. Preliminary analyses of baryon acoustic oscillation data from DAISY, released in 2024, suggested that the equation of state of dark energy may vary with time, a result that generated enormous excitement and equally enormous caution. If confirmed, it would revolutionize our understanding of the cosmos. But the result remains tentative, and the CMB will play a crucial role in resolving the question by providing a precise anchor at high redshift. The CMB constrains the early universe with such accuracy that any deviation in the late universe, driven by evolving dark energy or some other new physics, becomes detectable. And then there is the Hubble tension. This stubborn, persistent discrepancy between two ways of measuring the expansion rate of the universe has refused to go away, despite years of effort by the best observers and theorists in the field. On one side, the CMB. Planck measures the properties of the universe at recombination with exquisite precision. When those measurements are fed into the standard cosmological model and extrapolated forward to the present day, they predict a Hubble constant of 67.4 kilometers per second per megaparsec. This means that for every megaparsec, roughly 3.26 million light years, the universe is expanding at a rate of 67.4 kilometers per second. On the other side, the distance ladder, astronomers use Cepheid variable stars, whose intrinsic brightness can be determined from their pulsation period, to calibrate the distances to nearby galaxies. They then use Type 1a supernovae in those same galaxies as standardized candles to measure distances to galaxies much farther away. The relationship between those distances and the recession velocities of the galaxies gives the Hubble constant directly, without needing to assume any cosmological model. The most precise such measurement, led by Adam Rees and the SH0 collaboration using the Hubble Space Telescope, and later the James Webb Space Telescope, yields a value of approximately 73 kilometers per second per megaparsec. The difference between these two numbers, about 8%, may seem small, but the uncertainties on each measurement are now so tight that the discrepancy stands at roughly 5 standard deviations, a level of statistical significance that, in particle physics, would be considered a discovery. Something is wrong. Either one of the measurements contains an unrecognized systematic error, or there is genuinely new physics that the standard model does not account for. Independent methods add further intrigue. Gravitational lensing of quasars, studied by the TDCO-SMO consortium, gives a value of about 72 kilometers per second per megaparsec, supporting the distance ladder side. Baryon acoustic oscillation measurements from the Dark Energy Spectroscopic Instrument combined with Big Bang nucleosynthesis constraints, and entirely independent of the CMB, give a value closer to 68 or 69. Supporting the CMB side, the tension is real. And if it is not caused by a measurement error, then it points to something genuinely new in our understanding of the universe. Perhaps there is an additional form of energy that existed in the early universe, something that affected the expansion rate in the first few 100,000 years. Perhaps the dark energy is not a cosmological constant, but something that changes with time. Perhaps there is an unknown particle, a new species of neutrino, or some other form of radiation that has been hiding in the shadows. Or perhaps the answer is something nobody has thought of yet, something truly surprising. The CMB has been remarkably consistent with the lambda CDM model, the 6-parameter description of the universe that has served as the standard model of cosmology for over 2 decades. But the Hubble tension is a crack in that edifice, a hint that there may be physics beyond the standard model, lurking just below the surface of our best observations. And so the work goes on. The CMB has told us an extraordinary amount about the universe. It has confirmed the Big Bang. It has shown us the seeds of cosmic structure. It has measured the age of the universe to within about 50 million years. It has weighed the dark matter, quantified the dark energy, tested the predictions of nucleosynthesis, constrained the physics of inflation, confirmed the existence of the cosmic neutrino background, mapped the large-scale distribution of matter through gravitational lensing, and revealed the geometry of space itself. But it has also raised new questions. Questions that the current data cannot quite answer, which is why the next generation of CMB experiments is being built right now. The Simons Observatory, located at an altitude of 5,200 meters in the Atacama Desert of Chile, began taking data in mid-2024. It is an array of telescopes, both large aperture for high-resolution mapping and small aperture for wide-field polarization measurements, equipped with tens of thousands of cryogenically cooled detectors. Its primary goals include tightening constraints on the amplitude of primordial gravitational waves, measuring the masses of neutrinos through their subtle effect on the growth of cosmic structure, and mapping the distribution of matter in the universe through gravitational lensing of the CMB. The BICEP array, the successor to BICE P3, is currently operating at the South Pole. It extends the BICEP program to 6 frequency bands between 30 and 270 gigahertz, a dramatic improvement that will allow much better separation of the primordial signal from galactic dust and synchrotron contamination. With about 35,000 detectors when fully deployed, it represents a massive increase in sensitivity over its predecessors. The lesson of the 2014 dust controversy has been thoroughly absorbed. Future claims of a primordial B-mode detection will rest on multi-frequency observations, cross-checked against independent datasets, with every conceivable source of contamination modeled and subtracted. And then there is CMB-S4, the 4th generation ground-based CMB experiment. This is the ambitious one. Originally conceived as a single grand experiment uniting the entire CMB community, CMB-S4 has evolved into a partnership between multiple experiments and institutions, with telescopes planned for both the South Pole and the Atacama Desert. With close to 500,000 superconducting detectors, it will survey most of the sky with sensitivity and resolution that far exceed anything that has come before. Its science goals are sweeping: a definitive search for inflationary gravitational waves, with the ability to detect them if the signal is above a certain amplitude, or to rule out large classes of inflationary models if it is not; a measurement of the sum of neutrino masses, a census of galaxy clusters out to high redshifts, precision maps of gravitational lensing, and constraints on dark energy, modified gravity, and the physics of the early universe. CMBS-4 was recommended as a high priority by the National Academy's Astronomy 2020 Decadal Survey, the once-per-decade roadmap for American astronomy. However, its funding trajectory has been turbulent. In July of 2025, the U.S. Department of Energy and the National Science Foundation issued a joint statement indicating they had decided they could proceed with the project. But its scope and timeline have been revised. The current plan envisions a phased deployment, with initial instruments beginning observations in the late 2020s and the full experiment reaching completion in the early 2030s. Beyond the ground, JAXA, the Japanese space agency, is developing LightBird, a satellite mission dedicated to measuring the large-scale polarization of the CMB from the vantage of space. Scheduled for launch in the early 2030s, LightBird will observe the entire sky with 15 frequency bands, specifically optimized to detect the faint B-mode signal from primordial gravitational waves. Unlike ground-based experiments, a satellite avoids atmospheric noise entirely and can measure the largest angular scales on the sky, which are particularly sensitive to the inflationary signal. Together, these experiments represent an unprecedented investment in our ability to listen to the faint afterglow of creation. They will push our measurements to the limits imposed by fundamental physics, approaching the cosmic variance limit, the point at which we have extracted essentially all the information that the CMB has to give. And perhaps they will find the signal of inflation. Perhaps they will resolve the Hubble tension. Perhaps they will discover something entirely unexpected, something that overturns our current picture of the universe, just as the CMB itself overturned the steady-state model 60 years ago. That is the nature of science. Each answer breeds new questions. Each measurement opens new doors. The CMB has been our most faithful guide to the universe for 6 decades now, and it shows no sign of having exhausted its secrets. Consider, for a moment, what it means that you can detect the afterglow of the Big Bang with a television set. That the evidence for the origin of the universe is literally woven into the electromagnetic radiation that surrounds you at this very moment. In this room, wherever you are, photons that have been traveling for over 13 billion years, that were released when the first atoms formed, that have witnessed the entire history of cosmic evolution, are passing through your body right now. About 400 of them occupy every cubic centimeter of space around you. They have been traveling since before the first star ignited, since before the first galaxy coalesced, since before the first molecule formed, and they will continue traveling long after the last star has burned out and the universe has cooled to a temperature indistinguishable from absolute zero. They are the oldest light there is, and they carry within them the story of everything. When Arno Penzias and Robert Wilson heard that mysterious hiss in their antenna in 1964, they did not know what they had found. They thought it might be interference. They thought it might be pigeons. What it turned out to be was the voice of the universe itself, whispering its origin story to anyone patient enough and curious enough to listen. And we have been listening ever since. We have gone from a faint, unexplained noise to a full sky map of the infant cosmos. From a single temperature measurement at one wavelength to a power spectrum with 18 resolved acoustic peaks. From a rough estimate of a few cosmological parameters to a 6-parameter model that describes the universe to percent-level precision. From a 2-dimensional snapshot of the surface of last scattering to a 3-dimensional probe of the growth of structure across cosmic time. The cosmic microwave background is not just a relic of the past. It is a living, breathing data set, a message in a bottle thrown 13 billion years ago and still being decoded today. Every new experiment, every improvement in sensitivity, every reduction in systematic error reveals a little more of the message, a few more digits of the cosmic code. And we are not done decoding it yet. So the next time you find yourself looking up at the night sky or staring at the static on an old television set, remember what is hidden in that noise. Remember that the afterglow of creation is all around you, invisible, ancient, patient. It has been waiting for 13.8 billion years for someone to notice it. And when we finally did, it changed everything we knew about where we came from, what the universe is made of, and what our place is in the grand sweep of cosmic history. The faint afterglow of creation is still speaking, and we are still learning to listen. You have been watching the entire history of the universe. If you enjoyed this video, please hit the like button and subscribe to the channel. We would love to hear your thoughts in the comments below. Thanks for watching, and we will see you next time.